So this will be the fifth part of our discussion of Fourier series in ECE 343. Last time we gave a Fourier series example start to finish. We also talked some convergence issues associated with the Fourier series, concluding with the Dirichlet conditions. In this lecture, we're going to look very quickly at a few alternate forms of the Fourier series. We'll do a couple more examples, and then we'll conclude talking about Fourier series properties. Those Fourier series properties will look very familiar. They are very similar to what we've already seen as far as Laplace transform or Z-transform properties. So the different forms of the Fourier series, these are all going to be viewed in the Fourier series synthesis equations. We had just spent most of our time looking at the Fourier series through what is called the complex exponential form of the Fourier series. That is a form that says any old signal that is periodic can be represented as a linear combination of harmonically related complex exponentials. So that's what I'm identifying here. This is one that we derive through the orthogonality principle, and it's the form I prefer just because the mathematics associated with working with the complex exponentials tends to be simpler, at least in my view, than the trigonometric forms. We know, however, that a complex exponential can be converted into sines and cosines through Euler's identity. So if we chose, we could certainly rewrite the Fourier series synthesis equation not in terms of complex exponentials, but in terms of trigonometric functions, cosines and sines. And so the next form here that is shown is just doing that exact substitution. You go ahead and use Euler's formula, and we plug that in for the complex exponentials in that exponential Fourier series form, and we get something that's in a trigonometric form. We need to take a little bit different tact in here because it takes both a positive frequency and negative frequency exponential in order to get a real cosine. And so the sum here, you'll notice, goes from k equaling 1 to infinity plus the DC term out front. This trigonometric form, I think, is probably more intuitive as far as how our brains work. We think about taking, especially if the signal is real, a real signal as being a sum of sinusoids. That's a little easier to visualize than a sum of a bunch of complex exponentials, but it's a more awkward form mathematically to deal with. Doing things like integrating or differentiating the trigonometric form is just not as convenient as working with the exponential form. This particular one that I've just highlighted is the trigonometric Fourier series. It decomposes a periodic signal into a linear combination, a sum of harmonically related cosine terms and sine terms. We know that a cosine of a particular frequency plus a sine of a particular frequency can be combined into a single sinusoid that also can be derived using Euler's relationships. And so there is a compact trigonometric form so that we can write this expression for the synthesis equation, x of t, or periodic x of t, can be a DC term plus a linear combination of just single sinusoids, except for now what? We need some phase offsets in there in order to make it into single cosine terms. A cosine with the right phase offset can be the substitute then for this cosine plus sine where you didn't see a phase term in there. So there are two trigonometric forms, the first one being with a sine and a cosine and having 90 degrees between those two terms, or combining that sine and cosine together into a single cosine with the appropriate phase. Conversion between these forms, you can see table 6.1 in the textbook, and it's really I think user choice here as to which form you prefer. I definitely prefer the exponential form of the Fourier series. So let's go ahead and jump now into a few more examples of converting out the Fourier series expansion, and we'll conclude, like I said, the lecture with some properties. So the first one I'm going to look at is going to be one that we're going to make use of and look at again, especially when we get to the Fourier transform. But we are going to go ahead and look at a DC offset square wave. So I'm going to go ahead and draw parts of this guy. I'm going to go ahead and show it being on for some time and then off for some time and then repeating. And it's going to come out here and repeat with some period t naught. So this is my signal x of t. So I've got a signal x of t, and I'm going to go ahead and let it have some particular height, in this case of just 1. So it's going to be on for some particular time and then off and then on again. In this particular example, I think I'm going to go ahead and make it be a 50% duty cycle. So let's go ahead and make this a 50% duty cycle. 50% duty cycle, DC offset, square wave. So that's what we're going to be looking at here. We could certainly adjust that duty cycle. We'll do that later, but for right now, let's just leave it as a 50% duty cycle waveform. What does that mean? That means I could have something like minus T naught by 4 and T naught by 4. So this thing's on for a total width, right, of T naught by 2. Half of the period it's on, and then half the period it's off. And this is just a waveform that continues to repeat. If I take a look at this particular guy, I know that that period, T naught, right, is related to the fundamental frequency through the 2 pi. So 2 pi by omega naught is our period T naught, or that if we just solve for our frequency, our fundamental frequency, omega naught is equal to 2 pi by T naught. So we can make use of that as well as we go along. So I'm interested in finding the Fourier series coefficients for this guy. So I'm looking for my x of k's. I'm looking for those Fourier series coefficients. I know, because we've already derived this, that the Fourier series says that we can get those by taking 1 over t naught and then integrate over that period t naught, right? And then we're going to have our signal x of t, and then we will have that complex exponential e to the minus j k omega naught, and we'll have little t dt. So we're integrating out time and taking this time domain waveform essentially into the frequency domain. If I do a few substitutions in this just very quickly, we can do this as 1 over t naught, and I'm going to still have that integral over t naught, and I'm going to have my x of t. But what do I know about that exponential stuff? Omega naught is just 2 by t, so I can write this as a minus jk 2 pi by t dt. Why might I do that? Well, you'll notice that the terms out front, right? I have a 1 over t naught and I have an integration over t naught. Why not just include and make sure that I just do things in terms of t naught? That's certainly possible. You could do this later. It's not absolutely necessary, but it just gets it in terms of one parameter rather than two parameters, even though those two parameters are directly connected to one another. Okay, what did we talk about previously? We talked about previously that for the DC term, k equaling 0, the exponential inside that integral disappears, and that's oftentimes needing to be calculated separately, so we're going to go ahead and do that. K equaling 0 term in this case, we get what? We get x of 0 as being equal to 1 over the period, so I'm going to have 1 over t naught. And I get to choose where, in particular, I am going to go and do my integration here. And I think what I would like to do is I would like to integrate, right, from minus t naught by 2 to t naught by 2, something like that. So here's my t naught by 2 and minus t naught by 2. This is not the only choice, obviously, but it's a simple choice for the integration because it's 0 on the edges, and that means that the integral limits are really going to just go from minus t naught by 4 to t naught by 4, where that function x of t is just 1. So I'm going to go ahead and do that down here as well. I'm going to return to my integral, and I was going to go from minus t naught by 2 to t naught by 2, but over that interval it's non-zero only from minus t naught by 4 to t naught by 4. What was the signal over that range? It was 1, and then I'm going to have my e to the minus j k 2 by cap t naught little t dt. So I'm just integrating that exponential function. If I go ahead and do that, I'm going to get a, oh, well, I forgot one thing in there, I guess. We said k was equal to 0, right? So with k equaling to 0, this term becomes 1. And I'm just going to be integrating 1. So I'm going to have a 1 by t naught, integrate from minus t naught by 4 to t naught by 4 of 1 dt. That's going to give me a 1 by t naught, and I'm going to have my t there going from minus t naught by 4 to t naught by 4. And if I go ahead and do all of that, I'm going to get a 1 by t naught. First limit there is going to be t naught by 4 minus the other limit, so minus of a minus will become plus t naught by 4. That's going to give me t naught by 2, so that's going to be a t naught by 2, but there was also a t naught in the denominator before. Those t naughts cancel, and I'm left with 1/2. This is actually no surprise whatsoever. If we went back to the graph, right, what is the average value of a 50%? It's a 50% duty cycle square wave with peak amplitude 1. The smallest value is 0, and so we expect that DC value to come right there in the middle, right? We had 1 up here, we have 0 here, and so we do expect a DC value coming in there right at 1/2. So we just verified verified that I'm doing the math. So we got exactly what we'd expect in that particular case. For k not equal to 0, so all the non-DC terms, what do I get? I get cap x of k is being equal to 1 over t naught, and I'm still going to do it over the same range. So it's only non-zero from minus t naught by 4 to t naught by 4, at least over that period that I chose. And I'm going to have my signal in that portion. It was 1, and so I'm left with just what? E to the minus j k 2 pi by t naught little t dt. This is the integration of an exponential, so exponentials are pretty easy to integrate. I'm going to get a 1 over t naught, and then I have what? I have an e to the minus j k 2 pi by t naught, right? And I'm going to have my t up there, which I'll evaluate in the limits here in a minute. But then I'm going to have to divide by minus jk, right? And I'm going to have 2 pi by t naught. And I'm going on the limits minus t naught by 4 to t naught by 4. One of the things I will notice is that 1 by t naught out front is gonna cancel with the t naught in the denominator term here as I do that. Okay, so if I go ahead and do that and collect a few terms, I'm going to pull a few of those terms out front. I'm going to get a 1 over, and I just know where I'm going with this. So I'm going to pull the pi k out, and I'm going to have a j2 that I'm going to collect out there as well. And then I have my exponentials that are going to be something like an e to the j k. What happens? That top limit, for example, right? When I take a look at this guy, I'm looking at t naught by 4, and I put that in for my t value there. The t naughts cancel, right? I have a 4 in the denominator and a 2 in the numerator. That's going to just leave a 2 in the denominator, and so I'm going to get a pi by 2 in there. So I'm going to get a pi by 2 type of term in there. And so I'm going to have an e to the jk pi. Oops, need to get that back to my regular guy. So I'm going to have a pi by 2, pi by 2. And we will have in here a minus e to the minus j k pi by 2, something along those lines. It might seem like I just did that backwards, but I did reverse the order. I actually expressed the lower limit first and the upper limit second because of that minus sign in the denominator, this minus sign in the denominator, something along those lines. So you can check out the math on that. Why did I express it like this? Well, we can notice a few things. We'll notice that we have an exponential minus the negative of that exponential, and then there's a 2j out front. We can recognize that from Euler's form as being sine, and so we can get this in a simplified form as sine, and this is going to be k pi by 2 over k pi, something like that. So it's a sine x over nearly x type term. That's a really famous one. It's a really famous kind of form. That's related to something called the sinc function. And so if I could just get this slightly closer where I could have a divide by 2 there, well, that's just going to require me to have a 2 out front. This thing here in the middle is that thing called a sinc function. There's actually different forms for this. I'm going to go ahead and use the MATLAB form on this rather than the book form, just so that we could actually plug it into MATLAB if we want. I'll give the differences here in a minute. But in MATLAB anyway, MATLAB defines something. It defines something called the sinc function of x. And what is that going to be equal to? That's going to be sine of pi x by pi x. So it's kind of like a sine x by x. So you get the oscillations from a sinusoid, but you get a 1 over the argument, so a decaying envelope as to either side of the origin as your independent variable there gets larger. We'll draw some sketches, some real brief sketches here in a moment. So I could write this whole thing as a 1/2, and I'm going to have a sinc function in there of k by 2, something like that. That pi just, it gets absorbed into how MATLAB defines the sinc function. Turns out this isn't the only way to define the sinc function. This is just an annoyance because not every book uses the same form. Our textbook, for example, so our text does something like the following. It does sinc of x as being equal to, they define it as sine x by x. They don't use the pi in there. It doesn't really matter which one you do, but you do need to make sure that you use one particular form and not mix between them, because you'll be off by a parameter if you do that. The reason I choose the MATLAB one rather than the book one usually is just because I like checking out and plotting my results in MATLAB, and I don't want to have to rewrite my own function overriding the built-in function in MATLAB. So I prefer that definition that uses sine pi x over pi x. Usually, you just need to pick one or the other and go with it. So what does sine x over x, or the sinc function, look like? Sine we know is an odd function, right? So this guy here is an odd function. And, well, pi x is also an odd function. So we're taking an odd function and dividing it by an odd function. When you divide two odd functions together, you are going to get an even function. And so that's something we do know. We know the sinc function is going to be even. We know it's going to oscillate because of that sine term. And we know that it's going to have some decay because of that 1 over x kind of term. And so what ends up happening in here is we get something that looks a little bit like this. We get these kind of oscillations that are from that sine term, and then they get smaller and smaller and smaller by that 1 over x type of term in there. And it's an even function because we're taking an odd function over an odd function. This sinc function is found a lot in engineering, so if you've never seen it before, it's definitely one you want to get comfortable with. We will make large use or have a lot of application for this, especially when we get to the next section on the Fourier transform rather than the Fourier series. I think the reasons for that will become obvious. So let's go back to what we had up here. Oh, and I didn't mention this, but I probably should. If you look at the case of x equaling 0, so when x equals 0, you get sine 0, right? That's just 0 over 0. So you get a 0 over 0 indeterminate. In order for you to figure out what that value is, so if I look at something like sinc, right, of 0, you get kind of a 0 over 0 indeterminate. But if you apply something like L'Hopital's rule to that guy, you can see that it does go to a value of 1. So at that origin, which seems like a kind of problem point, it does converge to 1, and you can prove that through your calculus methods of using L'Hopital's rule. What I would say is that that's another reason for maybe using MATLAB's built-in function. If you just used your own, kind of anonymous function where you put in sine x over x, if you ever passed x equaling 0 to that, it wouldn't know what to do with that. It would return some kind of an error. So you'd have to have some error trap logic also with your function if you did that. The MATLAB built-in sinc function already does that for you if you choose to use it. Okay, so let's go back and just kind of remember what we were doing. We were looking at in this particular case, a DC offset 50% offset, or a DC offset 50% duty cycle square wave. So we had our x of t in there. It had some period t naught, and we found that those coefficients x of k were equal to, well, what did we get? We got a 1/2 sinc, right? K by 2. And we know sinc function at 0 gives us a half, and we had computed out in this particular case, right? We computed out that the DC value was a half. So it turns out in this particular case, I could leave the separate lines in there. I could do this as a 1/2 for k equaling 0, and I could do a 1/2 sinc, right, of k by 2 for k not equaling to 0. But because that second expression, when you put in k equaling 0, goes to the value we want, we could just write this whole thing as a 1/2 sinc function k by 2. So in this particular case, we get a very kind of a simple expression for our Fourier series coefficients. And in fact, you'll notice in this particular case, they are real. That's something that we'll maybe make a note of some properties that we're going to hit at the end of the lecture. So again, if you were interested in whether these guys were the correct values, what could you do? You could synthesize, right? You could synthesize in this particular case. You could synthesize. You could synthesize x of t with the x of k's, right? How do we do that? We know that x of t is equal to a summation, and we're going to have k going from minus infinity to infinity. Well, those minus infinities to infinities are probably going to be hard to do, so let's not do all of that. Let's just do an approximate and call it an estimate, right? Go from some minus cap k to some cap k of these xk, right? And then we have our e to the jk omega naught t. You know what the omega naught is. So we could resynthesize using this equation and make sure that we do reconstruct a fair approximation of our 50% duty cycle square wave. Let's quickly look at that. This is an example that's also shown in the book, so you can actually see these same plots. These are just the book plots. If you look at the top there, we see that the original waveform, that's the thing shown in gray, it's for a particular value t naught. Okay, so the particular value t naught here is pi. Really not that important. So the first top plot that you see there is just the DC approximation. So you see a straight line at that value half. We'd seen that. The next plot down, so I'm putting that in the center of the screen right now. That's a DC offset single sinusoid. So this would be cap k, right, being equal to 1. So I would include the cap k, or the little k, equaling minus 1, 0, and 1 terms in there. So I'd get DC plus a single sinusoid. And we see that single sinusoid comes in. And then if I do the next one and keep going and keep going and keep going, I see that this guy, as I include more and more terms, does converge towards that DC offset 50% duty cycle square wave. One of the things you'll notice there is the little ripples that you see towards that point of discontinuity. That's a behavior we've seen before. That's Gibbs phenomenon. And if you remember, anytime we have a truncated Fourier series, you get Gibbs phenomenon near points of discontinuity, near those sharp edges of that square wave. They don't go down in amplitude. You know, that overshoot turns out to be about 9% overshoot, but they do go down in power. So we do get those Fourier series convergence properties that the power of the error goes to 0 as we get more and more terms. This seems like a pretty good verification that our Fourier series coefficients were correct. So I don't think we have to spend a huge amount of more time on that. Okay, so let's look at one more example that's very related to this one. So I'd like to look at a slightly different one. We're going to fly through this one because it's a lot of the same. So in this particular case, I'm going to do another 50% duty cycle DC offset square wave. I'm just going to scoot it over a little bit, something like that. So I'm going to have here the period T naught come out so that the waveform is no longer even, right? It's just going to get moved over a quarter of its wavelength. What does that do? It starts at 0 and then ends at T naught by 2, then is 0 until T naught, and then it just keeps repeating. So we're still going to have a 50% DC offset square wave. But in this particular case, right, it's been shifted over just a tiny bit from X. I'd like to go ahead and find its Fourier series as well. Think about this for just a moment. If I just shifted over x, right, to get y, so what is y? Y is equal to x of t minus, right, t naught by 4, right? It's just shifting that x over by t naught by 4, something along those lines. If I just shifted that over by a quarter, am I changing the frequency content of that signal? I shouldn't be, right? Everything that made up that previous signal x of t, as far as kind of sinusoidal components, should still be there in this one. They're just shifted, right? They're just shifted, and that shift is nothing more than a phase shift in the sinusoidal terms. So what I should see is I should see something that comes out in magnitude spectrum being exactly the same, but whose phase spectrum changes a little bit. Certainly, you could go through the math on this and look for y of 0. What's the DC point? I'm going to just skip the math there because we can easily see it here. If this thing has a peak value of 1 because it's 50% duty cycle, we do see that that goes to half. That's easy. It's an integral 0 to t naught by 2 of 1, and you have the 1 over t naught out front because it's a Fourier series analysis equation, and you do get a half out of that. I'm gonna spend most of my time here for the k naught equaling to 0 term. So k naught equaling to 0, I'm going to be looking for my y of k's. What is that equal to? It's 1 over t naught. I'm going to integrate over a period. This time I'm going to pick a period that I'm going to go from, let's just go from 0 to t naught. And over from 0 to t naught, I have this signal y of t be non-zero only from 0 to t naught by 2. So that will change this to 0 to t naught by 2. What is it over that period? It is 1. And then I have my e to the minus j, right? k, and then we said that was a 2 pi by t naught t dt. So very similar kind of calculation that we had before. I'm going to have a 1 by t naught. I'm going to have my e to the minus j k 2 pi by t naught t divided by what? Minus j k 2 pi by t naught. Those t naughts are going to cancel, and I'm going to go 0 to t naught by 2, something along those lines. If I go ahead and do the substitutions on that and clean it up just a little bit, I will get a 1 over. I'm going to still have that pi k. I'm going to have a j2 just like I had before, and I will have a minus e to the minus jk pi plus 1, right? Something like that. I'm going to play a little bit of a mathematical, um, I guess, trick here for this other term. I'm going to pull out half of the phase of that first term, something along those lines. So I'm gonna write this just slightly different. I'm going to write this as I'm going to pull out e to the minus j pi by 2 k. That was half of this argument up here. I'm going to pull that out, and that leaves me what? I'm going to have a minus e, and I'm going to still have the other half, minus j pi by 2k. So I just split that guy in half. When I pull that half out, though, from the DC term 1, what do I get? I get an e to the j pi by 2k, right? Because e to the minus j something times e to the plus j something, you just add those exponents, that would give me e to the 0, that is 1. So I haven't changed anything here. I've just pulled out a little bit of a term. I'm going to have still down here that pi k term, and then I'm going to just move that j2 over here. And what I recognize is that that term on the right is the sine term that I was looking for. And in fact, it's still got that pi k. And so I can write this guy just in terms of my sinc function. And in fact, what I get is I get an e to the minus j pi by 2k, right? And I'm going to have, in this particular case, I'm going to have my sinc function then of k by 2, which was, if we go back, right, that was the essential coefficients that I had for my x function. And I think I might have forgotten a 1/2 out here as well. In this particular case, the 1/2 came out because of the normalizing of the sinc function. Let me just go ahead and put in the steps for that. Let's just make sure that we get it. So the right-hand equation here, right, this piece right here, right, is just the sine. So that is going to be a sine of pi by 2k. And then we had what? We had a pi k in the denominator, but we want to make that a sinc function, so we have to have the same argument in the numerators and the denominator. So I'm going to divide by 2, and this 1/2 in compensation. This piece here is the sinc. Okay, so yeah, we can see this guy coming out. It is an e to the minus j pi by 2k, right? And then I'm going to have that 1/2 sinc function. But what is that 1/2 sinc function? It's just the Fourier series coefficients that I had for x. So I'm going to put this in terms of x. These are my y of k's, okay? Y of k is just an exponential, right, times x of k. And if you think about that, that actually probably makes a little bit of sense. If I look at magnitude yk, right, that is going to be the magnitude of e to the minus j. So I'm looking at the magnitude spectrum, e to the minus j2 pi k, x of k. Magnitude of a product is a product of the magnitudes, and the magnitude of a complex exponential is just 1. So this whole thing equals the magnitude xk. And so this is actually a very intuitive result, right? That shifting that waveform x over to create a new waveform y, we just shifted it over, shouldn't change the fundamental kind of frequency components, the magnitude spectrum, the pieces that make it up. The only thing that would change would be phase. And if you look at this term here, that's all about phase, right? The magnitude of e to the minus j2 pi k is got magnitude 1, and it's got some different phase. So that extra term, that exponential term up there, is really just related to the phase shift, right? The time delay necessary to shift that function x to make the function y. Okay, we actually will see this as one of our properties upcoming shortly, that we didn't actually have to go through all that math. If you know a time domain signal is just shifted, you can actually use the shift property and write down the the resulting transform without any work. And that's one of the advantages of the properties, is that we don't have to go through all of these kind of calculations. So let's go ahead and take a look at the properties. I'm going to go ahead and make reference to the Fourier formula sheet that is available to you on Blackboard. So I'm going to encourage you to follow along with that sheet as well. I'm not going to draw these guys, and I'm not going to derive them because they are so similar to what we've seen already for Laplace and Z. Most of the properties are talked about in the book. They're also proven in the book. They're not hard proofs. And during our recitation section, if anybody wants to see a proof of any of these things, we're happy to do it. Let's talk more just about what the properties are and what they get for us. So this is just going to be going, if you take a look at that Fourier series formula sheet that's on Blackboard. There's 2 pages to that. We already covered the second page. The second page had the linear vector space, and it also had the orthogonality principle on it. We're dealing with the first page now. That first page is actually split into 2 columns. One column is for the Fourier transform. We haven't talked about that yet. The other column is for the Fourier series. That's what we're going to deal with here. And so it's got a recap of a lot of useful information in there. It has, for example, just this synthesis equation. This is one we've already derived. We derived that by the orthogonality principle, that any periodic signal can be represented as a linear combination of harmonically related complex exponentials, and that they have strength or size given by the Fourier series coefficient xk. You can find those x of k, right, through the analysis equation. That was derived by that orthogonality principle, and it's basically the inner product of our object of interest x with the exponential basis functions, the e to the jk omega naught t. That inner product takes a form that looks similar to power, so I get a 1 over t naught integrate over that period t naught x of t times the complex exponentials conjugate, so e to the minus jk omega naught t. Duality is something we're going to spend more time with. There's not a simple form of this for the Fourier series. We'll talk about that in the Fourier transform, so let's skip that for now, which is why it's blank here. Linearity is our first property, and linearity is something we've seen in every transform that we've dealt with so far. So when we had Laplace or Z, and in fact, when we look at these Fourier series properties, you're going to see very similar kind of properties for Laplace and also for Z. So these should look familiar. What's the linearity property? If I have a linear combination of time domain functions, I get a linear combination of their Fourier series, the transform domain representations. So AXT plus BYT would have a transform if you did the analysis on that. If you did an analysis, analysis of that waveform, you get a xk plus byk. I just take that same linear combination that I saw in the time domain, but I do it in the frequency domain. If I conjugate a signal in the time domain, I get conjugate reflection in the transform domain. Scaling and reversal. Scaling is that you either compress a signal or you expand a signal. But if I compress or expand a periodic signal, it changes its fundamental period, right? And that ends up getting absorbed into the parameter omega naught. So we aren't going to see an explicit scaling property. We'll make highlights of that difference when we get to the Fourier transform. The reversal part, though, pretty simple. If I reverse a time domain signal, I'm just going to get a reflection in the Fourier series coefficients. The shifting property, this is one we just saw maybe with our last example. If I shift a time domain signal, right, like we took our previous example, the first one was a signal x of t, and then we delayed it over by a quarter of its overall period, and we got a signal y of t. If I shift that signal, I can get the transform of that shifted version just by taking the original transform, right, times a complex exponential that's related to that shift. And actually, this is very similar to what you saw for Laplace as well. And that is the exact result that we got in the second example that we just completed, where we got the expression for yk. Yk was xk times an exponential related to that shift. We can also do things like shift our frequency domain variable, so x of k minus some k naught. And what happens is we get multiplication by an exponential in the other domain, in the time domain. This is very common kind of behavior that we see in Fourier, and that is related to this earlier statement of duality. Duality is really a principle that says there's some structural similarity between the analysis and the synthesis equation. So the synthesis and analysis equations have some similar structures, and so what tends to go in one direction also tends to go in the other direction with some slight modifications. That's what duality is all about, and we see it here in the shifting property. You shift in time, you get multiplication by an exponential in frequency. You shift in frequency and you get multiplication by an exponential in time. What goes in one direction tends to kind of go in the other direction. Differentiation, maybe I would just make the comment about this. Think about what differentiation would do if I took that guy through a Laplace transform. If I did it with a Laplace transform, I'd get s x of s. I'd get my transform times the frequency variable s. For Fourier, it's the same idea. It's just, what is my frequency variable? My frequency variable is jk omega naught, right? And actually, that should make some sense too. Where do sinusoids live in the S-plane? Sinusoids live at, if you think of S as being equal sigma plus j omega, they're on the sigma equaling 0. So right on that sigma equaling 0 axis, so the vertical axis. So we just get j omega. What frequencies omega are we looking at? We're looking at integer multiples of a complex of the base frequency omega naught. So I should get a jk omega naught, which is exactly what we get there. So this is just like the Laplace one, with s being equal to where sinusoids live in harmonically related sinusoids, jk omega naught. So again, very, very connected to something you've already seen before. You really don't have to spend a lot of time trying to recommit these to memory because they are so similar to what we had before. In an upcoming lecture, we will do a very in-depth set of examples where we're going to use these properties to help us in our analysis of waveforms to save time so we don't have to get caught up in a bunch of math that's not necessary. No time integration that we're going to worry about here. If you time integrate a periodic waveform, it goes off to infinity, so it just doesn't apply here. There's a convolution property. I'm gonna just highlight this. There is a form of convolution in the time domain. You can see there that it has a little circle around that convolution sign, and that's because we need a special form of convolution when we convolve two periodic signals. If I just did normal convolution on those things, it would go off to infinity because these periodic signals last forever. So there is a form of convolution that does all the convolution things. It takes one signal and it takes a flip and a shift of the other signal, slides one against the other, all that kind of stuff. But instead of integrating from minus infinity to infinity, it just integrates over the period. It is a convolution concept. It's called periodic or circular convolution. It's a convolution concept that's applicable or appropriate for periodic signals. If I circularly convolve, you can just think of this as convolve. If I convolve two periodic signals, x and y, I can end up getting their transform just through multiplication. We'd actually seen that before. So there was a Laplace transform property, right? That if I had x of t convolved with some h of t, for example, and you Laplace transform that, we got x of s, right, and h of s. Convolution became multiplication. That was one of the reasons we strongly motivated this idea of a Laplace transform, right? That difficult operation of convolution became a simpler one of multiplication. There's absolutely a similar kind of property here. We won't spend a bunch of time doing circular convolution. Just be aware that there's a form of convolution and its transform domain equivalent is multiplication. Maybe more interesting here is that we get the dual of this, right? What tends to go in one direction, it also goes in the other direction, which says what? If I convolve my spectra, and remember my spectra are discrete here, so this is a convolution sum. If I do a discrete time convolution on my spectra xk and yk, it corresponds to multiplication in the time domain. So convolution in one domain, multiplication in the other domain. Correlation is something I'm going to spend more time in once we talk about the Fourier transform. Correlation is just a form of convolution, but let's not worry about it too much. The last property that's in here is parseval's. We actually saw parseval's when we took our original estimate k term, and we let k go off to infinity, and then we looked at the minimum error. And what did we find? We found that the power in the time domain, right, was preserved in the frequency domain. That whatever the signal's time domain power was, right, we could get that same value by summing up the square magnitude of all the Fourier series coefficients. So we had seen that before when we looked at the minimum error as we let it go off to infinity, right? So all of those properties are available to us. Let's go back to the lecture, and we're going to finish this guy out. I have one more example, and then we'll be done for the day. I would like to do one more Fourier example that is going to have some help for us at a later example, and it's also just a pretty sweet one. So let's do one last example. So in this particular example, I'm going to take a look at a function which I'm going to call a periodic delta train. So I'm going to give some kind of weird notation here. I'm going to call it delta tilde. That tilde above is just kind of our reminder that it's going to be a periodic replication of a delta train. I'm going to subscript it with a period just so we know what the period of that delta train is, and it is a function of time. So let me go ahead and give a definition of how we might get this. So it's going to be a summation. I'm going to let that sum go on some variable like n going minus infinity to infinity, and it's just going to be a delta of t minus n cap t naught, something like that. If I plotted what this guy looks like, right, take n equals 0, I would get just delta t. I know what delta t is, right? That's a delta function at 0. Put little n equaling 1, I'd get a delta of t minus cap t naught. So that's just a shifted delta function to the right by t naught. So I would get a delta function. That's a t naught, right? That's the n equaling 1 term. This one was the n equaling 0 term. If I do n equaling 2, I'm going to get 1 shifted over by 2 t naught. So I'm going to have here something 2 t naught. And I keep going. And I also have all the negative values. So if I went out here to n equals minus 1, right, I would end up going to minus t naught. That's my n equals minus 1 term. And it keeps going off to the left. So I just get a bunch of delta functions, right, each separated by a total time t naught. It's a periodic delta train. I would like to go ahead and think about the Fourier series on this. This is a waveform, right, that is periodic. It's a continuous time periodic signal. And Fourier tells us that continuous time periodic signals should have a Fourier series representation. I should be able to represent this as a sum of harmonically related sinusoids. I want you to think about that. So we are going to try to represent that. We're going to represent, right, with a sum of harmonic sinusoids. When you think about that, this is something actually almost mystifying. What does a sinusoid look like? It looks like this. It's this oscillating waveform, right, that is 0 almost never. I mean, it hits 0 every once in a while, right? But almost everywhere it's non-zero. We're going to take something like that and then double the frequency and all of these guys, and we're going to keep adding them up, right? And we're hoping we can get a waveform that is non-zero at a point and then 0 everywhere. If we can do that with a Fourier series, it really is saying something pretty special, right? We're taking continuous waves, these sinusoids, and we're adding them up to get some kind of waveform that's 0 everywhere except for at little isolated points where it flies off to infinity. Actually, a pretty amazing kind of premise, or an amazing kind of an idea. So let's look at what the Fourier series would be here. So we have our signal x sub t naught of t tilde. That is my time domain waveform, this periodic delta train. And we could say that we could go through a Fourier series analysis on that, and we should get the transform domain. Notation in this book, much like all other books that I've seen on introductory signals, takes the time domain waveforms as being lowercase, and it takes the transform domain as being uppercase, whether the transform is a Laplace or a Z or Fourier. So I'm going to take the uppercase of delta, so I'm going to call this cap delta tilde, and it is a function of k. So I'm just going to put that function down in the denominator. We could have put it like a bracket k, something like that. That just gets a little awkward. So I'm going to go ahead and just put it as this. So I'm going to look for these Fourier series coefficients, which I'm going to call cap delta of k. So what is cap delta of k equal to? Cap delta, right, of k is equal to 1 over the period, right, integrate over the period of my signal, delta tilde sub t naught of t, right? And I have an e to the minus j k omega naught t dt. Let's go back to the waveform, right? Back to the waveform. I get to choose what period I integrate over, and I'm going to pick here going from minus t naught over 2 to t naught over 2, something along those lines. So if I take a look at this particular guy, right, I'm going to go from minus t naught over 2 to t naught over 2, and I'm going to integrate my delta t naught over that. And what you can see is that there's just a single delta function on that. So if I come down here, I know that this is going to be an integral 1 over t naught. And I was integrating, right, from minus t naught by 2 to t naught by 2. I'm actually putting in definite limits of integration. And over that interval, delta tilde is just a single delta function. It's just delta t, not shifted, nothing, just delta at the origin. And I have my e to the minus jk omega naught t. This is one of the few cases where I'm violating my general argument that you have to find DC terms separately. And it's just because this is just a little bit of a different kind of integral. We've seen this integral before, right? We know that if I have a delta function times anything integrated, that we can sift out. So I can use the sifting property here. I'm going to use sifting property, and I'm going to be able to integrate that with almost no effort whatsoever. So I'm going to have 1 over t naught, and I'm integrating a delta function times something. I'm just going to sift out that function evaluated when the delta was non-zero, which is at t equaling 0. So I sift out e to the minus jk omega naught t at t equaling 0. That's e to the j0, that's just 1. So I sift out a value of 1 on that. And what am I left with? I'm left with my Fourier series coefficients here being a constant, and the constant is just 1 by t naught. So that's simple. That doesn't matter what k value is. My cap delta sub k tilde, right, is being equal to 1 by t naught. They're just all constant. If I was going to plot those guys out, right, I would have a value 1 by t naught at DC. I'd have 1 by t naught at k equaling 1, and at k equaling 2, and at k equaling minus 1, and so forth. This is my cap delta tilde sub k. So this is kind of an interesting example, right? Take a look at what we had. We had a continuous time delta train, right? And we looked at what it is in the frequency domain, and it's a delta train of its own sort in the frequency domain. And furthermore, you'll notice that the amount of content, right, is flat. Right? We do have to use harmonically related sinusoids. It was a periodic waveform. Everything must share the same period, otherwise we wouldn't get a good synthesis. So we only can include harmonics, DC, the first harmonic, second harmonic, third harmonic, all the way out. But we need all infinity harmonics, and they all have exactly the same content, right? They all have exactly the same height. It never decays off. And part of that never decaying off is part of what allows us to get that time domain signal, the delta t's that have an infinite amplitude in there. Okay, so this spectrum, we might notice, right? The spectrum here, spectrum is flat, which is kind of neat. And what we see is we see delta tilde sub t naught of t, right, goes to a Fourier series, right? That is going to be my cap delta tilde of k being 1 over k. It's like a delta train, right? This guy is a delta train, continuous time delta train in time. And this goes to something that is also delta train like, but you might call this a discrete delta train in the frequency domain. Now, if I use the Fourier series synthesis equation, right, what do I get? I'm going to just rewrite what we had and think about this. So we had a delta tilde sub t naught of t, which we defined as what? We defined it as just this delta train. So k equaling minus infinity to infinity of delta t minus, right, k t naught. I think I did that on n before. Let me just go ahead and do that. Maybe avoid some potential confusion. So we'll do it something like nt naught. What does Fourier series say? Fourier series says you can reconstruct a waveform as a sum. That sum is on all of our frequency components, k equals minus infinity to infinity of my x of k's, or my cap delta of k's, my Fourier series coefficients, which in this case are just 1 by t naught, right? And then they weight these exponentials, e to the j k omega naught t. So I can make, right, a delta train as a sum of harmonically related sinusoids, right? A infinite train of delta functions can be made out of an infinite sum of harmonically related complex exponentials. I don't know. That is just a cool relationship to me. That is cool. That is a cool relationship. You think about the nature of those deltas, right? We had seen that and just an emphasis of that. We had these sharp, spiky guys that were zero everywhere, and we're building it up out of stuff, right, that looks smooth, these exponential, these sinusoidal pieces. Really something to contemplate. That's enough for now. Next time we are going to do a much more in-depth kind of set of examples where we're going to utilize the properties to help us carry out the Fourier series analysis and hopefully avoid some tedious mathematics. So that'll be next time.